These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. What is light?
Light is an electromagnetic wave.
Good, good. That's a good answer. So what is it that's oscillating in the electromagnetic wave?
What's oscillating? The electric fields and the magnetic fields.
That's right. That's what it means to be an electromagnetic wave. Okay, good. So can light experience interference?
Yes.
Yes. So that's a key point. If light was not a wave, it couldn't have interference. So can two light waves ever add together to form zero?
Yes.
Yeah, that's destructive interference. Notice how different that is from particles. If two particles hit a point, they never magically turn into zero particles. There's no such thing as destructive interference for particles. But if two waves hit a point, it can be as if there was no wave at all. So I'll say that again. If two particles hit a point, it's never as if there were no particles hitting that point. But if two waves hit a point, it could be just like no waves hit that point if they have complete destructive interference. That's one of the most important differences between waves and particles, one way you can tell the difference between them. With waves, 1 plus 1 can equal 0, so to speak, if you have destructive interference. Okay. All right. Do you know what this is a picture of?
I know those are like slits.
So what do we call this setup?
I don't know.
So this is what's called the double-slit experiment.
Okay.
So this is one of the main topics that's likely to come up on the next exam, the double-slit experiment. You can see that's a pretty obvious name for it because we have two slits here. So let's make sure we understand everything on the page here. So what's this?
A wall?
Yeah, it's just a barrier of some type. The key thing is you would not want to make this out of glass. That would defeat the whole purpose. What's this?
A slit.
That's one of the slits, and here's the other slit. What's this?
Another barrier?
Now, here we don't just want a barrier, we want a screen, right? Because we want to see where the light is hitting.
Okay.
It helps to draw a central axis like we did on our optics problems. Okay, do you know what happens when you do the double slit experiment? What do you see on the screen?
I'm assuming only a certain amount of light can be let through each slit. And so your screen, you only see like light at those specific spots.
You're saying that there would be light here and light here.
Yes.
And it would be dark everywhere else.
Yeah.
Okay. Now I think about your common sense about how light works. You know that if this was water wave, the water wave would spread out once it passes through the slit, right? Okay, so that turned out that guess was incorrect. We're not just going to get light directly in front of the slits. The light is going to spread out all over. But what we are actually going to get is we're going to get a pattern of dark and bright spots. For example, we could have a bright spot here, then bright spots here, then bright spots here. Actually, these would be fringes. Bright fringe, bright fringe, bright fringe. And between them would be dark. Why? Why are we getting that? Well, think about the light, say, that goes through here. let's say we look at the light that hits this point. So some of the light from this slit will hit this point, but also some of the light from this slit will hit this point. As we said, the light won't just go straight horizontally through the slits. It will go in all directions. Do these two light rays travel the same distance?
No.
No. Which one, is this going the longer or the shorter distance?
Longer.
Now, because it's going a longer distance, so one thing I should have emphasized is that we're going to start here, in order to get this experiment to work, we start with light rays that are all in phase with each other. That's not the way normal light rays work. The light rays from my light bulbs here are not automatically in phase with each other. They're all jumbled up. But if you use, say, a laser, that would generate a coherent beam of light rays where all the light is in phase with each other. So would you agree then that when the light is at these 2 points, they would be in phase with each other? When this is cresting, this would be cresting. And when this is troughing, this would be troughing. So if we start with coherent light rays, they'll be in phase when they move through the slits. But do you agree they don't have to be in phase anymore when they reach the screen because they travel different distances? Mm-hmm. Okay. So even though the light rays are starting in phase, do they have to end up in phase? No. No, maybe they will and maybe they won't. Okay. So why does it matter whether they're in phase or not? Because that will determine whether they end up with constructive or destructive interference. So if it's constructive interference, what would we see on the screen?
Light.
And if it's destructive interference, what would we see?
No light.
Yeah, so what I was going for is, if it's constructive interference, you see a bright fringe, and if it's destructive interference, you would get a dark fringe. Okay? So let's say that the two light rays moved the same exact distance. Would they end up in phase or not?
In phase.
In phase, because they started in phase. But that doesn't apply here. Suppose that the two light waves went a different distance. Suppose that the first one traveled, say, 6 wavelengths, and this one traveled, say, 9 wavelengths. Do you think they would end up in phase or out of phase?
They'd be in phase.
Because they're differing by a whole number of wavelengths.
Yeah.
So these two would still end up in phase. Suppose this one went 6 wavelengths and this one went 9.5 wavelengths. Then would they end up in phase or out of phase?
Out of phase.
Because this extra half wavelength puts this light wave half a cycle behind this one. Alright, so would this be a dark or a bright fringe?
This would be a dark fringe.
Right. How about this?
Bright.
How about this?
Dark.
Okay, good. So what matters then is what we could call the path length difference. Do you understand what I mean by path length difference? That's how much further this distance is than this one. What matters is whether the path length difference is an integer number of wavelengths or an integer number of wavelengths plus half a wavelength. Okay. So what are we going to get here on the principal axis, the central axis? Will this be a bright or a dark fringe?
Right.
How do you know?
Because they would both move the exact same amount.
They both have the same distance to travel.
Yeah.
How do you know? Because of the symmetry. Since this is in the center, symmetry tells us, because by definition this principal axis is halfway between the two slits. So symmetry tells us they travel the same distance. So what would be the path length difference for these two rays?
0.
So obviously if they started in phase, they would end up in phase. So notice this is the only point that you can predict without extra information. Without extra information, we don't know whether any of these other points would be bright or dark. But we know that the central spot must always be bright. Okay, good. So I've labeled these as bright, dark, bright, dark. Verbally, we could say this is the central bright spot. This is the first bright spot above the center. This is the second bright spot above the center. This is the third bright spot above the center. This is the first dark spot above the center. This is the second dark spot above the center. But if we're going to solve math problems, we need to be able to describe these mathematically, not just verbally. Do you know what the mathematical description for this is? Did you get that far? How do we describe this point mathematically?
I don't remember.
What's the variable we use for this? So this would be called the m equals 0
Okay.
bright spot. You might have seen that in class. And this is called the m equals 0 dark spot. So what would this be?
M equals 1.
Bright spot. And this?
M equals 1 dark.
Good. So let's do a couple more.
M equals 2 bright. And then M equals 2 dark.
All right, good enough. How about this?
M equals...
I suppose if we wanted to be fancy, we could call it -1, but it's actually good enough just to call it another m equals 1 spot. So we can use m equals 1 for both of these two. So what would this be?
M equals 1 bright.
And this?
M equals 2 dark.
And this?
M equals 2 bright.
Good. Another way to describe this verbally, this is the 0th order bright fringe. This is the 0th order dark fringe. This is the first order bright fringe. So if someone says third order, how would you translate that into math?
M equals 3.
Good. Would you agree this is the first bright spot above the center?
Yes.
And what's its m?
1.
Would you agree this is the first dark spot above the center?
Yes.
But what's its m?
0.
So do you see how people could get confused by that? Notice the first dark spot does not have an m of 1. If someone was in a hurry and they said, focus on the first dark spot above the center, it would be natural to say, oh, m is 1, because there was the number first in the sentence. But when you actually draw the picture, it doesn't work out that way. So that's something to watch out for. So, for example, if you were looking at the second dark spot above the center, what would that mean in math?
M equals 1.
Yeah, second dark spot does not mean m equals 2. Second dark spot means m equals 1. Suppose that you were looking at the second bright spot above the center.
M equals 2.
So there the m makes more sense. The safest thing is actually to draw the picture out so you can tell the difference between them. Okay, so the order does not necessarily tell you kind of the order. All right. All right. Did you pick up from class or from the videos, what do we call this distance? What's the symbol for that? Did you pick that up?
D.
That's right. D for distance. Do you happen to remember what we call this distance?
L.
That's right. Good. How can we describe the location of these points? How can we describe their location? Well, there's actually two different methods. One method is to describe the location with theta. Let's look at, say, this point here. Draw the angle theta for that point.
So this point?
Yeah. Draw what would be the angle theta. We haven't talked about theta, but I just want to check. Do you remember that term from class? Do you know what would be the theta angle for that point?
I don't know.
We'll go over it together.
Yeah.
So this is the theta angle.
Okay.
So how do you form the theta? Well, first of all, you draw this central axis. That's one of the main reasons we drew the central axis. And then you draw a line from the spot to where the central axis intersects the barrier. The one thing you don't do is you don't do anything with the slits. That would be the mistake. The angle is not an angle that's being made with the slits directly. It's being made with the point halfway between the slits. So for example, theta for this point would then be this. So for any particular double slit experiment, is there one theta or many thetas?
Many.
Yeah. For any particular double-slit experiment, is there one M or many M's?
Many.
For any particular double-slit experiment, is there one L or many L's?
One.
So that's a difference between them. Of course, we could change L by changing this distance, but that would be a different experiment. For any particular experiment, is there one D or many Ds?
One.
Just one. Of course, we could change the D by making a new barrier, but that would be a new experiment. So notice theta and M have a different status than L and D, because there's automatically many thetas and M's, but only one D and L. All right, try drawing the theta angle for this point. Good, okay. Might be better to use a dashed line for that. So would you agree theta is a way of describing the location of the points? For example, as you move further from the center, what happens to theta?
It increases.
That's right. I suppose technically we could call these positive thetas and these negative thetas, but that turns out not really to be necessary. So we can use a positive theta for both above and below. So every theta actually refers to two different points. The theta above and the theta below. So the further we are from the center, the bigger theta is. So the point is, if you were given theta, you could figure out exactly where on the screen we were talking about. So that's one good way to locate the points. But there's another way that we could locate this point, which is much more intuitive. Instead of locating it by theta, we could just tell directly what this distance is. Do you know what the symbol is for that distance?
Y.
That's right, yes. That's logical because we normally consider this to be a vertical screen, and we normally use Y for vertical distances. So for any double-slit experiment, will there be one Y or many Ys?
Many Y.
Yeah, it's like theta or M, because there's a different Y for every different point on the screen. So label Y for this point.
Let me just read this.
So I forget which point. So for this point, this would be the Y. Notice again, it has nothing to do with the slits. The distances are relative to the central axis. In fact, we're never actually going to use the actual location of the slits in solving the problem. They're just for realism. Their only significance is to get this distance here. Again, technically, maybe we don't need to call these negative Y's. We can just say the Y is always positive. Okay, so I think those are the variables that you're going to need for this type of problem. So then we need to have equations that tell us where the bright and dark spots are going to be. We already know where this will be, but the other ones we don't know. Well, remember that technically we already know how to figure that out. All we have to do is, for each point, we have to figure out the path length difference. And if the path length difference is an integer number of wavelengths, what will we get?
You would get constructive interference.
And what would that look like?
Bright spot.
Yeah, a bright fringe. And if the path length difference was an integer number of wavelengths plus half a wavelength, then what would we see?
A dark fringe.
That's right. So all we should do is do some math to figure out what the path length difference is for different points, and that's just a geometry problem, right? We'd have to figure out how long this distance is and compare it to this distance, and then compare that to the wavelength. What's the symbol for wavelength?
Lambda.
So that's another symbol that you'd often use on these problems. So the textbook does that, but the formula is a little bit tricky to prove. I don't think you'd have to prove it on the test, so we'll just say what the equation is. So it turns out that for the double-slit experiment, the constructive interference equation is d sine theta equals m lambda. And the destructive interference equation is d sine theta equals m plus 1/2 lambda. What's theta for this point?
0.
Yeah, 0. Because it's 0 degrees above the central axis. What's the sine of 0?
The sine of 0 is 0.
That's true. Yes. Whenever you write one of these equations here, you have to say what the possible values are for m. What's the smallest possible value that would make sense for m here?
0.
Does that really make sense? Let's see. So if m was 0, what would theta turn out to be?
0.
Yeah, because the sine of theta is 0. Well, we already said that's what we want. We want this central bright spot to be here. So it makes sense here for m to be 0. And what would be the next m?
1.
And then 2, 3. M is what's called an index. So it's important whenever you write this equation to also write the possible indexes. How about for this equation? Is it possible for m to be 0 in this equation?
Yes.
It doesn't mess us up. We just have d sine theta is half a wavelength. There's no reason why d sine theta can't be half a wavelength. So what's the smallest possible m here?
0.
And then
1.
2, 3. So in these two cases, they have the same possible indexes. But later we might see other equations where m can't be 0. I was already taking for granted that m could be 0 here. Did I mess this up? It should be. What should be m for this point?
0.
Yeah. So maybe I wrote that incorrectly. And this one should be.
1.
So I think I made the same mistake I was telling you not to make. The first dark spot below the center has an m of 0, not 1. And the second dark spot below the center has an m of 1, not 2. I think I just made the same mistake I told you not to make. Okay. By the way, so it turns out that the left-hand side here is just the path length difference. D times the sine of theta is the path length difference between the two different rays. There's a geometry proof of that in the textbook, but I don't think you have to prove that. So notice this is just saying that when the path length difference is a whole number of wavelengths, we get constructive interference, just like we said. And when the path length difference is a whole number of wavelengths plus half a wavelength, then you get destructive interference. So the only part of this that we didn't quite prove is that this is the actual path length difference. But otherwise the equations make sense. Now, remember, how do we talk about the location of the spots? One way to talk about the location of the spots is with their theta. But what's the other way to describe the location of a spot?
With their y value?
That's right. So we should have an alternative form of the equation that's in terms of y instead of theta. So here's the alternative form for constructive interference. Of course, the indexes are the same in both cases. So take a guess as to what this equation should be.
dy over L equals m plus 1 half theta.
With the same possible m's. Good. Technically, this equation is only an approximation. Technically, this is only an approximation that works when theta is small. But you're not really expected in this class to judge whether the angle is small or not. So in this class, how do you know which of these two equations to use? Well, let's say that you're doing a problem that mentions theta. Which equation should you probably use?
The one with theta in it?
Yes. And let's say you're doing a problem that mentions y. Which equation should you probably use?
The one with y in it.
All right, so like I said, technically this is only for small angles, but you don't actually have to check whether the angle is small enough. You can just assume that if the problem is talking about y, they set it up so that the angle is small enough to use this approximation. So if the angle is small, so technically this should be an approximate sign, but I'm not going to bother drawing that in because we can just treat it like an equality for this class. So if they mentioned y, use this equation. If they mentioned theta, use this equation. Good. So what are the SI units for D?
Meters.
How about for lambda?
Mm.
What are the SI units?
Nanometers? Meters.
Which one?
Meters.
Meters. Why did you say nanometers? Well, it's true that it's common to use nanometers, but that doesn't make that the SI units. Any distance, the SI unit is always meters. What's the SI units for Y?
Meters.
And for L?
Meters.
Because they're all distances. What are the units for M?
No units.
Yeah, no units. It's an index. It has no units. All right. Technically, you do not need SI units in this formula. Technically, all you need is consistent units. So if you wanted, you could put these all in nanometers, or all in centimeters, or all in millimeters. However, most people find it easiest to convert into meters. So my suggestion is that you should pretty much always just convert everything into meters. Because these will be in very different units to start with. This would tend to be in nanometers, this would tend to be in meters, and this might be in centimeters or millimeters. So just put them all into meters. Okay, let's try this problem. This will be problem 1.
Okay. So I'm gonna start by drawing it. D equals 2 centimeters, so that's so this is
calculator on this if you need to.
So there's okay, so it's bright. So that means it's constructive. So we're going to use d sine theta.
Maybe you should try this step without a calculator.
Really? No. Okay, fine. Okay, I'm going to change this then to 2 times. So sine theta plus 500.
I can see I didn't set this problem up very well because the angle turned out, the angle is going to be absurdly small in this case. So it's not a very realistic problem. But anyway, let's just go through the steps.
So theta is 0.0029?
Yeah, so that's kind of an unrealistically small angle, but that's just because I just made up these numbers off the top of my head. Okay, good. Okay, that's good. Why did you use the sine theta equation and not the y over L equation?
Because we're solving for the angle location.
That's right. And why did you use the constructive equation and not the destructive equation?
Because it's a bright fringe.
As you wrote down. So those are the two things you need to think about in these problems. Constructive or destructive, and which of the two equations should you use? Okay, good, that's right. So notice there's a lot of unit conversion on these problems, so you have to watch out for that. What is light?
Yeah, wave.
Yeah, so light is a wave. Now, as we've talked about before, this was something that was very controversial for a long time. Some people thought light was a particle, some people thought light was a wave. A lot of people maybe thought it was impossible to tell. Like we talked about, it seems very hard to study light. It seems so intangible. So for example, I think Isaac Newton thought that light was a particle. And partly because he was so prestigious, for a long time after Isaac Newton, most people thought that light was a particle. But eventually, pretty much everyone changed their mind and decided that light was a wave. How do we know that light is a wave?
Has wave-like characteristics.
Like what? How do we know it has wave-like characteristics?
It follows the wave equation.
Which equation is that?
V equals lambda times frequency. Frequency
okay,
times
that's true. That's true. But the problem is, it's really hard to see its frequency and its wavelength.
Yeah.
So that can't be how we actually know it, because the wavelength, the frequency is so high and the wavelength is so low, we can't actually observe them. So how do you think scientists actually prove that light has wave characteristics? What's an experiment that you could do that would prove that light has wave characteristics? What's an experiment we could do that proves that light has wave characteristics?
I'm not sure. Like they somehow visualized it? I don't know.
Think about it for a couple more seconds. What's an experiment we could do that would prove that light has wave characteristics?
I don't know.
Do you remember? What's the key difference between a wave and a particle?
A wave versus a particle.
Well, most
the
important.
particle is like a little, like a single thing, whereas a wave is like continuous.
How does that affect our observations, though? Remember that we said the key difference is waves can have destructive interference.
Oh.
Right? There's no way a particle could have destructive interference.
Yeah.
So if two particles hit a point, it's never like there were no particles hitting it. But if two waves hit a point, it could be like nothing hit it. So we could prove that light was a wave if we could prove that it had constructive and destructive interference. Well, what's an experiment that we could use to prove that light has constructive and destructive interference?
This one?
Yeah, so that's what I was going for. This is the experiment.
Okay.
So this is the experiment that changed everyone's mind. So as I was saying, in the late 1600s, Newton thought that light was a particle. And after that, I think most scientists agreed, yeah, maybe Newton's right, maybe light's a particle. But then in 1800, someone did this experiment. So that the particle theory was the top theory for about 100 years. But then in 1800, Thomas Young did this experiment. And do you see how this experiment proved that light must be a wave? Because if it was a particle, there would be no reason to have this pattern of dark and bright spots. The only way to explain why we're getting dark and bright fringes is that there's constructive and destructive interference. Okay, so it's good to see the historical importance of this experiment. This is the experiment that proved that light was a wave. Of course, there's many other experiments you could do, but this was the first one that was used. That's why it's oftentimes popular on exams. Okay. By the way, remember, we shouldn't get too pleased about that, because it turned out that later on, Newton was partly right as well. It turns out that in other experiments, light has particle characteristics. We haven't actually studied that yet in the course. So the scientists were patting themselves on the back a little too early here. They thought they had proved that light was a wave, but later it turned out that in other experiments it behaves like a particle. But at least this proved that sometimes it behaves like a wave. Okay, let's try this problem too. By the way, does your class have a lab component?
Yeah.
So have you done this experiment in lab?
No, I think we're doing that this week.
I see, we'll be doing it later.
I think.
Okay.
I'm
Okay.
assuming. We haven't done it yet.
Yeah, so I've never actually done this experiment, but you'll be able to see for yourself whether light really does have wave characteristics. Have you been doing experiments with lenses and mirrors?
Yeah. I mean, I've just been like following what the handbook says, but like,
Okay.
I don't know how much I actually picked up from it.
Oh, that's too bad.
Yeah, well, because they only give us less than 2 hours to finish it all, so we're pretty much just trying to answer everything instead of like actually doing it.
They give you 2 hours and then they kick you out?
Yeah.
Huh.
So you have to finish within 2 hours, so it's really rushed. So this is... actually this one. D equals 0.5. Millimeters in your meters, so that's sorry, I'm trying to do the math in my head. 1.5 is 3 halves. So you divide it by 3 halves, so you multiply by 2/3 times 2/3. I don't know, just kidding. This isn't right. But anyways, that's the answer.
Okay, we should try to do the calculations a little bit more, because you might have to do these calculations on the test, since you can't use a calculator.
Okay.
I'm not sure why you're erasing everything. Most of what you wrote was correct.
Are you sure? Okay. Okay, well it's 2, so times divided by 3 halves. So is it 4/3 times 10^3? Is it? Oh no.
So this is what you have. The first thing you should do is this. You're getting confused by combining the power of 10 with the numbers. Now this part you did correctly, so this is 2 divided by 3 halves. You're right, 2 divided by 3 halves is 2 times 2/3. So the 4/3 is correct. And what should be your power of 10?
-3?
That was the part that you got incorrect. You were accidentally moving the 10/3 from the denominator to the numerator without changing the power of 10. Also, remember what was the question asking us for?
The wavelength.
The wavelength. So which power of 10 would make more sense for a wavelength of light? +3 or -3? Yeah, actually even this doesn't make sense. Is this too big a number or too small?
Too big.
Yeah, but that's just because I just made these numbers up out of the top of my head, so they don't actually happen to come out right. So these numbers don't actually happen to come out with light that's anywhere close to the visible range, because I just made them up from scratch. But this is the right method for solving this. If this was a realistic number, then you would get light that was in what range? Yeah, so it would be in the 400 to 800 nanometer. Oh, no, I guess we still messed up though, didn't we? So what are the units on this answer?
Millimeters?
Yeah, okay. That's right. It would probably be most useful though to have your answer in meters, so then you could change it into nanometers if this was a real problem. I guess we don't have to do the whole thing all over now, but what I would say is, what you did is you converted this length into millimeters.
Yeah.
But I think it's probably a better habit to convert all the units into meters.
Okay.
Right? Because then it'll be easier to convert into nanometers at the end. Let's go ahead and do that. So how many meters is this? Let's work that out. That's right. Oh, so it's not turning out to be so bad. Now let's change it into nanometers. Show me on paper how you would go from meters to nanometers.
Yeah, so...
How many nanometers are there in a meter?
10 to the 9.
Not 10. Oh, yeah, okay, 10 to the 9. It looks like a 7. All right. Okay, and now write that as an ordinary number. Without the scientific notation.
Well, okay, so 4 divided by 3. Is like 1.3.
Because it's 1 1/3.
1.3 times 10 to the 3rd. So 3, 0, 0.
So actually, I got pretty close to the visible range, right? So is this, what range would this be in?
This would be above. This would be above infrared.
It might still be in infrared, I'm not sure. It's above red, anyway. It might be in infrared. Okay, so actually these numbers didn't turn out so bad. They were pretty close to being reasonable. So my recommendation on these is put everything into meters, and then at the end, if it's wavelength, you should translate it into nanometers to see if your answer makes sense. What is the wavelength of red light?
700
What are the units on that?
nanometers.
How do we know that? You can't look at red light and see the wavelength. This is way too small. How do we know that's the wavelength of red light?
They use this experiment.
Yeah. Do you see, how could we use this experiment to find the wavelength of red light?
You shine red light into it, and then you see, and then you use like one of the spots.
Yeah, you do it just like we did on this problem right here, basically. You can pick any spot you want as long as you get the right M for it. Okay, so that's another interesting thing about the double-slit experiment. All this time we've been talking about light as being in the 400 to 700 nanometers region, but we didn't say how the heck we know that. Well, you can use an experiment like this to actually... So the cool thing about this experiment is, this experiment that Thomas Young did in 1800, not only was he able to prove that light was a wave, but at the very same time that he found that light was a wave, he was able to actually figure out the wavelength of the light. Again, that's a pretty impressive achievement considering how small a nanometer is. There's no way you can actually see the nanometer, but at least, so supposing that he was good enough at geometry to work out these equations, he could actually then work out what the wavelength was for the different colors of light he was using. So, one thing that we should point out here that you might not have realized then, would you agree that if you shine one color through the barrier, you'll get one pattern of dots? But then if you turn that light off and you shine a different color, you'll get a different pattern of dots. Because different colors will give you different wavelengths, and different wavelengths will give you different Ys. So that's something I haven't been mentioning, but notice normally you do this with only one color. That's called monochromatic light. Normally you use only one color, otherwise you get a whole mixture of dots. So the simplest way to do this is with only one color of monochromatic light, so that you get a clear answer. On the other hand, you could use multiple colors, and then you would get different bright spots next to each other. One bright spot for red, and then next to it another bright spot for a different color. Notice what happens as you increase the wavelengths. As you increase the wavelengths, do the spots get more spread out or condensed?
More spread out.
Because the Y would increase. So if you shift to a higher wavelength, which is shifting towards the red end, so the redder the light gets, the more the spots spread out from the central axis. So it's possible you might see a more advanced problem where there was more than one color being used, and you just have to realize that the two colors will result in different patterns of spots. By the way, remember that we want the light to initially be coherent and all in phase with each other. One way you could do that is by using a laser. Another way you could do that is you could pass the light first through a narrow single slit. By passing it through a narrow single slit, that enforces all the light that goes through here is going to be in a very coherent beam with each other. And then the light will spread out, so it's still able to go through here. So I just want to point out, if you start with a single slit and then you have the double slit, that doesn't change the results of the experiment. This single slit here can just be ignored. This is just being used to get a coherent beam of light. It doesn't change how we solve the problem. There's other experiments that only have a single slit, and those have different equations. But this is still a double slit experiment. This is not the experiment here, this is just creating the coherent beam of light. Okay, so let's move on to another type of experiment. Another type of experiment we could do, since doing the double slit was so much fun, maybe we could do multiple slits. We could have more than one slit, so we could have a whole bunch of slits that the light is going through. So now we'll move on to the multiple slit experiment. Normally here we have a bunch of slits very close to each other. So this is also called, another name for this, what type of apparatus do you use for a multiple slit experiment? You can use what's called a diffraction grating. A diffraction grating is something with a whole bunch of slits or lines right next to each other that light can go through. So diffraction grating is the same thing as the multiple slit experiment. So what about our variables? Can we still use the same variables? Well, we can still use m, we can still use theta, we can still use L. We need to reinterpret what D stands for. Take a guess what D might stand for in the multiple slit experiment.
The distance between the slit and the center line?
The distance between...
Or between each individual slit?
So it's the distance between a pair of slits. So, if each of these lines is a slit, then this distance would be D. And this distance would also be D. And this distance would also be D. And this distance would be D. And that distance would also be D. So notice, is D the complete length of the diffraction grating? No, it's just the distance between slits. So it's really the same exact definition as from the multiple slit experiment. In the multiple slit experiment, D was the distance between slits, and between the adjacent slits, and here D is also the distance between two adjacent slits. However, they don't usually tell you D. What they might do instead is they might say, the grating has 2,000 slits over 4 centimeters. So let's see if we can figure out, how would you figure out D from this?
D would be 2,000 divided by 4. So 500 centimeters? Wait, no. 2,000 divided by 4. So... okay, hold on. So, yeah, I'll do it here. No, I'll do it here. Okay, so the gradient, the grating has 2,000. So 4 divided by 2,000?
Good. Let's get an answer for that.
So D will be 0.002 centimeters.
So what units do we want our answer to be in?
Meters?
Yeah, or centimeters.
Or
So
centimeters?
first you were doing 2,000 divided by 4. But how can you see that was wrong? Because what would be the units on that?
Slit per centimeter?
Which is not what we're going for. We want centimeters per slit. That tells us how many centimeters there are next to each slit. So we want to do 4 centimeters over the 2,000 slits. This will tell us how many centimeters are adjacent to each slit. So you did this as a long division. You might have to do this on the test. So what I would do instead, maybe, is I would reduce the fraction first. What does that reduce to?
2 over 1,000 or 500.
So that would have made our life a little bit easier on that problem. So you got 0.002 centimeters?
Yeah.
All right, so you did do that correctly, but it might help to reduce the fraction first. However, what units do we probably want this to be in to work with the other numbers?
Meters.
So you probably want to convert it into meters. So what would that be?
0.002 times 10 to the negative 2.
Good. Okay, so that's the type of unit conversion that you're likely to need. Okay, so they're usually not going to tell you D for these problems. You need to figure out D. Now, what's the equation going to be for the diffraction grating? Notice that now the analysis is going to be much more confusing because now there's going to be a bunch of different light rays hitting each point. There's going to be a light ray from all of these different slits. So there seems like there's many different possibilities for constructive and destructive interference. So it gets too confusing for me to understand how it comes out. But in the book, they came up with an equation anyway. And the nice thing is, it's the same equation as the one here. So again, for constructive interference, we have our same equation. D sine theta equals m lambda, or dy over L equals m lambda. And again, m starts at 0. It's not really obvious at all that this is the right equation anymore, but it turns out that if you think it through like they do in the textbook, we end up with the same equation for constructive interference as we did here. However, it turns out that destructive interference becomes much more complicated in this case. So this equation doesn't apply for destructive interference anymore. So I'm not going to, I don't think you're going to be tested on destructive interference for the diffraction grating. For the diffraction grating, you would not use this equation for destructive interference. It's more complicated than that. So we won't write down an equation for destructive interference. Here we'll just focus on the constructive interference. So is this problem 3? Let's try problem 3.
Is centimeters per line, so it's 1 over 2. And it's a second bright fringe away, so equals 2, and theta equals 1. So we're to draw it out, be like that, and that, oops. This is equals 0, equals 1, equals 2. Yeah, and then D equals and you want to find the frequency, which is related to wavelength by and we know theta, so we can use d sine theta.
So what units?
Okay, so that's in centimeters.
I guess you could get away with that, but your life will be easier if you work with different units.
Well, then our lambda would just be centimeters. And
Yeah, I guess that's okay. All right, fair enough. I shouldn't have said anything.
Can I use my calculator?
Okay, yep.
And then I guess I can convert it to meters. So equals 1.61 times 10 to the square meters. And then frequency would be 3 times 10 to the 8 divided by 1.61 times 10 to the 2. So that's which is
Now, when you're so what units did you plug in the wavelength in?
nanometers. Oh, it should be meters, huh?
So I think it's a good idea to put this into nanometers to check whether it's realistic, but when you're going to use that in another equation, it's got to be in SI units.
Okay. So in meters, that would just be 1.61 times 10 to the 5. To -7. So like 1.86 times 10 to the 15 hertz.
Okay, good. Okay, so you can see one thing you should highlight in your notes here is watch out for the units. There's almost always going to be units problems on these because we're dealing with a bunch of lengths that are going to be naturally in different units. Remember, there was also a problem in the homework that you did, or the unit conversion that messed us up. So that's something to highlight in your notes to watch out for on the test. So by the way, is this light visible?
No.
Because how many nanometers is it?
161.
Yeah. And the lowest visible would be 400. So it's still good to figure this out to see. So again, I kind of set the problem up wrong a little bit. I just made up the numbers out of my head, so they didn't happen to come out in the visible spectrum. One thing that's worth realizing is this is a good way to check yourself to make sure you're in the right range. Your answer will not necessarily come out in the visible range, depending on how careful the instructor was, but it should be somewhere in the 10 to the -7 meters range, right? It certainly shouldn't be something like 10 to the -20 meters or 10 to the +5 meters. We'd almost certainly have made a mistake there. By the way, so what's the realistic range of light, 400 and 700 nanometers, what's the realistic frequencies? So visible light, it's worth maybe putting in your cheat sheet, visible light is in the 10 to the 14th. What are the units on this? Hertz. So visible light is in the range of 10 to the 14 hertz. That's a good way to check yourself. This actually came out a little bit away from 10 to the 14th because again it's not quite visible. But this is a good way to check your answer. If your frequency of light comes out to be 10 to the 20th, it's pretty sure you made a mistake. Or if your frequency comes out to be like 15, it's pretty sure you made a mistake. It should be somewhere in the 10 to the 14th range. Okay. Okay, so you calculated the D, and so again, the key thing here is to be careful with the units. Good. So now let's look at a different type of situation where I have light. So what we dealt with so far is the double-slit experiment and the multiple-slit experiment. What's another name for the multiple-slit experiment?
Grating.
Diffraction grating. In fact, that's the term that's usually used. So the other main topic in this chapter is what's called thin films. Thin films is another place where we get these interference effects. So let's say that we have air here and air here, but here we have, say, a soap film. So here we have a thin film. It can be made of many different substances. We might say it's a soap film. Soap is mainly water, so the N might be close to 1.3. What is going to happen to the light when it hits this surface of the film? Well, we know that whenever you hit a surface, some light is reflected and some is transmitted. So some of this light will be reflected back in this direction, and some will be transmitted and keep going through. Now notice, if I was going to draw this realistically, this light ray should really be right here. But I'm going to pretend it's down here just so they don't get on top of each other. And what's going to happen to the light that hits here?
Some of it's going to reflect and some it's going to go through.
That's right.
But it wouldn't be, oh, just kind of.
So some will be transmitted,
Yeah.
and again some will be reflected. So that light will be reflected to here. Now again, realistically, this light that was reflected by the second surface would really go back along the same exact path it came in on. But so that we can think about them, I'm putting them at different places. So then, if you're looking at the reflections, your eye will get hit by both of these light rays. And in reality, they'd both be along the same exact horizontal line. So you'd see both of these light rays coming back. Well, notice here we have again a chance for interference, right? Either constructive or destructive interference. Why is there a chance for interference? Well, one reason is because, again, we have a path length difference. Again, there's a path length difference, so there's a chance to have different types of interference when it hits your eye. Okay, in the homework, this is an equation that you can definitely prove using things we've talked about so far. But the homework didn't really seem to have any problems based on proving the equation. It was all based on using it. So I'm just going to write down the equations. So there's an equation for constructive interference. Which is this. Equation for destructive interference, which is this. It's definitely possible to prove these equations, but like I said, they didn't do that in the homework, so let's focus first on just how to use them. You know what D stands for?
The difference in length?
Of the paths?
Yeah.
Close. What it stands for is how wide the film is. So would you agree that actually 2D is the path length difference?
Right. Yeah.
Because this has to go here and come back. So this 2D is actually the path length difference. Okay.
Oh, is that a 2?
Oh yes. Yeah.
Okay, I thought
2.
it was a Z. I was like, what? I wasn't sure. Okay.
Okay. So we can see why it might make sense to put in a 2 because that gives us the path length difference. Okay, so we haven't quite explained why these equations actually work, but these are the correct equations. M here again is an index. Does it make sense for M to be 0 in this equation?
Yes.
If M was 0, what would D have to be?
0.
But that then wouldn't really be a film, would there? So what I mean is it doesn't make sense for M to be 0. An M of 0 doesn't make sense because then there wouldn't actually be a film. So this is a case where the smallest possible M is 1. Notice in all our previous cases, I've been telling you should always write down the possible M's. That might have seemed pretty boring because we kept writing down the same list every time, but it's not always the same list. This is an equation that starts with a different possible M. Does it make sense for this M to be 0? Because D doesn't have to be 0 then. So with this m, this list still does start at 0. So this is the only case where m has to start at 1. Okay. Now, normally, so let's say that we hold d constant. Then, as m increases, what's going to happen to lambda?
It will decrease.
Because otherwise this couldn't be an equation.
Yeah.
If we're increasing the right-hand side of the equation with m, we have to decrease it with lambda. So, what's the meaning of m? What this equation tells us then is that there's certain wavelengths that will experience constructive interference. So when you put in m equals 0, does that give you the biggest wavelength or the smallest wavelength?
Biggest.
Yeah. So m equals 0, that would be a very small m, would give us the biggest possible lambda. So when m equals 0, this equation will tell you the largest wavelength that experiences constructive interference. And then when m equals 1, that gives you the next biggest wavelength that experiences constructive interference. Then when m equals 2, that gives you the next biggest wavelength that experiences constructive interference, and m could just keep on going on indefinitely. Now, probably only a few of those m's will give you visible lambdas. In fact, there might only be one m that gives you a visible lambda. Or there might be only 1 or 2 or 3 that give you visible lambdas, and the other ones will be outside the visible spectrum. So notice the interpretation of m here is quite different than in the double-slit experiment. Here, the m was referring to different spots. Here, the m is giving us different wavelengths that will experience constructive interference. So what would happen if we shine white light at this film? What will this person see? Now remember, white light contains all the wavelengths, right? White light contains all the wavelengths. But which wavelengths will the person see? The person will, so all the wavelengths will be reflected, but is the person going to see the wavelengths that are reaching him with constructive interference or with destructive interference?
Constructive.
You're only going to see the wavelengths that hit your eye with constructive interference. Any wavelengths that are destructively interfering, they're going to dim out, and you're not going to see them as much. So here, the light looks white. But do you agree that once it's reflected, only 1 or 2 colors are going to be reflected? In fact, typically only 1 color will be in the visible range. So this is the reason why, maybe if you've ever looked at a soap film, oftentimes it has a bright color to it. Or if you ever look like at an oil slick on the ground, oftentimes it's very colorful. And the reason is, even though it's getting hit by white sunlight from the sun, even though all of the light from the sun is hitting the film, only one wavelength is being reflected with constructive interference. That's why a thin film often appears colorful. Okay. So if the problem asks you to find the biggest possible wavelength, that's a coded way of telling you to do what in the equation? The biggest possible wavelength occurs how mathematically?
M is smallest.
And what's the smallest possible m here?
0.
Or suppose they wanted the biggest possible wavelength that got destructive interference.
And M would be 1.
That's right. So when they say biggest wavelength, that's a code for putting the smallest m. That's why you need to know what the smallest m is. In this equation, the smallest m is 1, but in this equation, the smallest m is 0. Or let's say that we were using only one wavelength. Let's say we were using only one wavelength, and you wanted to find the smallest film that would have constructive interference for that wavelength. How would you find the smallest film that has constructive interference for one wavelength?
For one wavelength.
Yeah.
Smallest film, so that would have the smallest m.
So what would you plug in for m?
0.
So notice, trying to find the biggest wavelength is equivalent, similar to trying to find the biggest d. So here I was saying, what do you do in a problem where you're supposed to hold d constant and make lambda big? You put in a small m. The other type of question they could ask is where they're only shining one color. And they could ask, how do you get the smallest possible d that will give you constructive or destructive interference for that? Well, to get the smallest d, you would plug in
Smallest m.
yeah, smallest m. Because as m increases, what happens to d here if lambda is constant?
It increases.
Because they're on opposite sides of the equation. So those are typical ways that the questions tend to be worded. Something else I want to point out is that in real life, many soap films don't look like this. In real life, many soap films might look like this. That is, they have different widths at different points. They have different widths at different points. Doesn't that mean that different wavelengths will be constructively interfering at different points? The wavelength that constructively interferes here might be different than the wavelength that constructively interferes here. So that again explains why you might see a rainbow when you look at an oil slick, because the slick of the film might have different widths at different points. So you could get a whole range of colors that you're seeing. Oh, one more point. What are the SI units for this number?
Meters.
And this?
Meters.
Now this is another equation though where you don't need SI units, you just need consistent units. And I would give you opposite advice here. With these equations I said put everything into meters. But actually here, these two numbers are likely to be pretty close to each other if you look at it. They're both going to be very small because this is a thin film. So you're actually probably just as well off here just working everything in nanometers. In this equation it's probably best to put everything in nanometers. But what units are best in these equations?
Meters.
Probably meters because the numbers are so far from each other. What do you think this stands for?
Index of refraction?
Whose index of refraction?
The films?
Yeah, the film. And what does this stand for?
Wavelength of light?
In air. Good. What number of problem is this?
4.
Thanks. Okay, let's try this.
So it's constructive. 3 is 2t. And you want to find the smallest thickness. So the smallest thickness will equal 0.
Think about how you went from this line to this line.
Yeah. 39 meters?
500 divided by 6 is 30?
Is that it? No, just kidding. Wait, 500. Oh. 4, 5, 6, 7, 8, 8. So 83.3 nanometers.
Okay. Good. So notice here it's convenient just to leave everything in nanometers. So the trick here that a lot of people won't realize is when they say the smallest possible d, that means the smallest possible m, because d and m move in the same direction. Good. So the division you did was 500 over 6. Let me just show you a little trick. I think it's a good habit to get into the habit of reducing before you divide. What does this reduce to?
250 over 3.
I think this would be an easier division for people to do. So that's a good habit if you can't use a calculator to first reduce and then do the division. I think you did that correct. Okay, so that's a typical type of situation here for a thin film. So in these equations, what units are probably best to use?
Meters.
In here?
Meters.
In here?
Meters.
In here?
And
Notice this is the constructive interference equation for the double-slit experiment. Does it have m or m plus 1/2? How about for the thin film? What does the constructive interference equation look like?
M plus 1/2.
So that's a trap that someone might fall into easily. I think by now you're probably used to thinking that the 1/2 equation is always destructive. So I know you wrote it down correctly in your notes and you did the problem right, but notice if someone doesn't check their notes and they just go on memory, they can easily misremember this equation because it seems like it's the opposite of the earlier equations. We didn't really explain why the 1/2 is in the constructive equation here. The book does the proof for why there's a 1/2 here, but anyway, that's something to watch out for. So remember that the equations kind of look different for the thin films than they do for the double slit. For the slit experiments, the 1/2 is in the destructive equations. But for the thin film, the 1/2 is in the constructive equations. So what you should do, I guess your midterm is next week, so you should be starting to put your cheat sheet together for the test. So this part of the board here, this is what you need in your cheat sheet for this week's material. These are the key equations that you're likely to need on the test. And the safest thing is to actually look them up. Because remember, if you rely on memory, you might misremember this equation because the 1/2 might make you think it's destructive when it's really constructive. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. or you can just use the link in the annotation. Thank you.